Hello, good morning. I'm going to discuss the topic conversion of NFA to DFA. Now, what we say here is finite automata. There are two types. One is deterministic and non-deterministic. Fine. So, deterministic in the sense from one state on one input. We write it like this. Deterministic means from one state on one input going to only one state. So this is another input. Let us take it, we have two states. From one state on one input is going to only one state. We say it's DFA. Okay. Now whereas non-deterministic finite automata is from one state on one input going to multiple states, we call it as non-deterministic finite automata. Now what we say here is the language which is accepted by finite NFA, non-deterministic finite automata, there exists a DFA which accepts the same language, which means that we say NFA which means that we say NFA is equivalent to DFA. Okay, so that is the reason we say equivalence of NFA to DFA. Now there is an equivalent cycle actually. So from NFA you can get an equivalent DFA, but vice versa is not possible. Given a DFA, you cannot get an equivalent NFA. But if given a DFA, we can get an equivalent regular expression. Okay. Now, given a regular expression, you can get an equivalent NFA epsilon. Okay. Given NFA epsilon, you can get an equivalent NFA. From NFA epsilon also, you can get an equivalent DFA. Okay. Now, this is the cycle. Given a non-deterministic finite automata, you can get a DFA, but DFA you will not get an equivalent NFA, but you can get an equivalent regular expression. From regular expression we can get NFA epsilon, from NFA epsilon you can get an NFA. Okay, now what we see here is you will be given a non-deterministic finite automata and you have to get an equivalent DFA. Now first let us see what is non-deterministic finite automata mathematically defined. We write it NFA, which is mathematically defined as m equal to q sigma delta comma q naught comma n. It's a phi tuple where q stands for set of states which are defined for that automata, and sigma is input alphabet. What are the possible inputs that are taken for that automata is being described by an alphabet called sigma, and delta stands for transition, and q naught is initial state and f is set of final state. There will be only one initial state but can be many final state. Okay, and transition we write it like this. Okay, so whereas DFA we write it like this: DFA equal to m dash q sigma delta dash, to differentiate between NFA and DFA, q naught comma f. Okay, q is set of states, sigma is input alphabet set, and the inputs that are there for NFA will also be the same input symbols for DFA as well. Initial state will also be same. Okay, the only difference comes in transition. Here we for differentiation only we are writing NFA transition as delta and DFA transition as delta cap. Okay, now let us take it the automata, and so we take automata q0 on input A, q1 on A, and q1 on B. Okay, now this is the given automata, and from this automata what can we say here is, from this automata we can say there are two states. This is given NFA, this is given NFA, and you have to get equivalent DFA. Okay, now step 1, what we are going to do it here is, now first for the given NFA we prepare a transition function. Now how you write a transition function is delta n. There are two states, one is Q0 which is initial state, and other one is Q1 which is the final state. There are only two states, and the input alphabets are A and B for this given NFA. Now we write it, this is NFA transition table. Now Q0 on A, it is going to two states, one is Q0 comma Q1, and Q0 on B it's not going anywhere. Q1 on A it's going to Q1, and Q1 on B it's going to Q0. Okay, so this is the information we have from given NFA. Now what we are going to do it is, in step 2, okay, the only difference comes in transition, right? So NFA transition and DFA transition we are going to make, whereas NFA transition is, we write it like this, delta is Q cross sigma gives 2 bar Q, this is NFA, and DFA is, we write it delta dash Q cross sigma gives Q. Okay, now how we are going to do it here is, we are going to convert equivalent, we start with initial state of NFA which is Q0. So we take Q0 as initial state, Q0 as initial state of DFA, and we do transition on, we do transition from initial state, so which is Q0, which is Q0. So now in second step we do prepare a transition table which is delta cap, and the input symbols of NFA will also be the same input symbols of DFA. Now this is DFA transition table. So this is step 2 is, we are constructing a DFA transition table. So we take initial state of NFA is same as initial state of DFA, and to differentiate between NFA and DFA we are writing delta dash, and the input symbols are A and B. Okay. Now from the given NFA, Q0 on A, we write it like this, delta dash of Q0 on input A. Okay, so from Q0 state on input A. So from the given information what we got it here is, it is going to two states Q0 and Q1. Now the trick here is, we use a method called subset construction, and now what we do is, we don't treat them as two different states, we treat them as one single state. This we are going to merge it, Q0 Q1 as a new state, and that new state is here. Okay, now it is a single state. We don't treat as two different states, we treat as one single state which is Q0 Q1. Now for this new state Q0 Q1, we are going to do transition for this. Okay, now the states will be whatever the outcome that has come from on transition. For the new state you have to do transition on input AV. Till how long you have to do it? You have to do it until no new state has been formed. Okay, now we also do delta dash of Q0 on B. We don't have anything else, so we write it here 5. So there is no new state, so that is the reason. What are the new states that we are going to get? We write it here on the states. Okay, and for that new state you have to do transition. Now for this new state Q0 Q1, so we write it like delta dash of Q0 Q1 on A. We write it like this, delta of Q0 on A union, so we write it Q0 on A union delta of Q1 on A. Okay, so what is Q0 on A? It's Q0 Q1 from given NFA union. What is Q1 on A? Q1 on A, it's also Q1. So you got it. When you're doing union, we write it only once, which is Q0 Q1 only. So we got it here, Q0 Q1 only. It's not a new state, so we are not writing it here. If it's a new state, we have to write it here and do transition on A, B. Okay, now we have to do it for delta dash of Q0 Q1 on B. Delta dash of Q0 Q1 on B. So we write it like this, delta of Q0 on B union DFA transition is equivalent to NFA transition of this thing. So delta of Q1 on B. What is Q0 on B? It's 5. What is Q1 on B? It's Q1 only. So now what we do it here is, in this thing we write a new state called Q1. So as it is a new state, we have to do transition for Q1 as well. So when we do Q1 on A, it's what? Q1 on A, it's not defined. Okay, and Q1 on A, it's not defined, and Q1 on B is also not defined. Q1 on A, it's Q1 only. Sorry, Q1 on B, it's not defined. Now there is no new state. We stop constructing transition because the outcome of Q0 on A is Q0 Q1. We merge it into a single state, and for that new state we are going to do transition. Okay, now finally what we got it, this is a transition table for a given NFA. Now this is the transition table for the given NFA. Now what we are going to do is, we are going to draw a DFA diagram. Okay, how many states we have? We have 3 states. Initial state Q0 and another state which is Q0 Q1 and Q1, this is Q1, and another state which is Q1. Okay, now there are 3 states. This you look at here, there are 3 states. So Q0 on A, it's going to, we give a mapping on A, and this is initial state, and Q0 on B, nothing is here, and Q0 Q1 on A, it's going to Q0 Q1, and Q0 Q1 on B, it's going to Q1. Q1 on A, it's going to Q1, and Q1 on B, it's not going anywhere. So we create a null state, and Q0 on B and Q1 on B. Okay, and what could be the final state? In the given NFA, Q1 is the final state. So wherever Q1 is there in the states, you mark it as final state. Now this is the equivalence DFA of given NFA. This is the equivalent DFA of given NFA.